Okay, so this is a new model for 12D. You might not realise that 12D has been involved in stormwater pretty much since version 1 with the, well, maybe 1, maybe 2. Nobody's really sure where the version 1 came out, but with the pipeline module. But they always relied on their strength to interface with other products to do all the analysis. So for a number of years, he used drains, XP Swim, XP Storm, Mike 11, HEC-RAS, dozens of others, but it wasn't until probably version 6 or version 7 with Owen's first rational formula design, which was the introduction to the love-hate relationship with the drainage network editor, by the way, when 12D started doing their own dynamic drainage, their own drainage analysis. So since then we've added the 1D dynamic drainage analysis in V9, the 2D dynamic drainage in V10 and V11. Wastewater we've added in V10, and that'll expand, I think, over the coming 12 months to 2 years of the life of version 12. And then the one we're going to talk about now, the wastewater package, which is a new add-on for version 12. Okay, so it's a hydraulic analysis and water quality behaviour of pressurised pipe systems. It's an extended period simulation, so it can be a snapshot, a static analysis, but because it has time, it's considered a dynamic analysis. Uses continuity and Bernoulli to solve the network. And a network consists of a series of pumps, pipes, valves, junctions, storage tanks and reservoirs. So you can model pressure reducing valves, pressure sensing valves, pressure sustaining valves, pressure breaker valves, pretty much all the valves you could want, multiple types of pumps, only circular pipes, and then tanks, junctions and reservoirs. It can handle very large networks. It's a memory-based model. It could, you could easily run a 50,000 pipe network. Might be tricky to look at the results, but you could run that. It's applicable for planning, so for capital improvements or rehab plans and so on. Can be used for design to evaluate cross connections, to size pumps and valves and so on. Can use for operations, for leak detections or for optimising electricity usage, so you can work out the cost of running pumps. Or asset management and ADAC, and you'll probably hear something about ADAC at some stage during this conference. It can also track the flow of water. Well, what it does is track the flow of water in each pipe. It tracks the pressure at each node, tracks the height of water in the tank and the hydraulic grade line at each node, the concentration of a chemical species throughout the network. So by a bit of jiggery-pokery, if you take a reactive chemical, apply some factors to it, you can get the water age in the system. So every 1 second, a drop of water becomes 1 second older, and you can look at how long the water's been in your network. It can also, the water quality can also be used to track a flow by a non-reactive constituent, give it a concentration of 100, and then at any node in the network, you can look and see how much water came from a specific tank. So if you've got multiple tanks throughout your network, you can see what percentage of flow is coming from different tanks. Okay, it's accessed. It's currently as part of the drainage network editor. It's accessed by picking the hydrology method of water supply in the D&E. The units it supports are both metric and US. Flow units are pretty much everything, litres per second to cubic metres per day, cubic feet per second, gallons per minute, acre feet per day, whatever your units might be your favourites. Okay, so junctions. Your node can be either a junction, a tank or a reservoir. So junctions are points in the network where water enters or leaves the network. It's just a point in space. A junction can have a demand or a demand pattern, so that's a constant flow from the network, or it could be a source of input if the demand was negative. It could also have a time pattern associated with that demand, or there can be, or it can be an emitter, which is like a sprinkler that might be associated with an industrial building or a commercial firefighting facility, or it could be an irrigation system as part of your network. Okay. The other type of node you could have is a tank. Obviously, a tank can be any shape, and a tank has it can be mixed. So the flow can be a fill and draw type tank, which would be completely mixed. It could be a baffle tank, which would be a first in, last out type tank, where the water is never considered to mix in the tank. It could be a standpipe, which would be a last in, first out type of system, where the water enters and leaves from the bottom of the tank, and again the plugs don't mix. Or it could be a two-compartment reactor. So reservoirs are really large dams where the water head doesn't vary very much from over time, although you can put in a time pattern if you need to or you want to. And the other optional component is water quality. So we can have a tank, a reservoir or a junction can be a source of water quality. So it can be a concentration or a mass flow or a set point or a flow paste constituent. Then we define a baseline strength and we can have a quality pattern with it. So that's an optional component that we can add. Links in the system can be pipes. Pipe conveys flow, but it can also have an effect on water quality, where you can have a reaction against the pipe wall, so chlorine reacting with the corrosion protection, or a biofilm in the pipe or something. Again, that's an optional thing. A pipe can also be a check valve, so you can restrict the flow to one direction, or you can turn a pump on or off. So you can look at the rehab, where you might want to disconnect part of your network. You can just simply turn the status to closed. Then the other two hydraulic items are the pumps. Pumps are considered a link, even though they're physically sort of not a part of a pipe. But they've considered a link because they change the flow by imparting energy to the water and raising the hydraulic grade line. And valves are also considered links because they can change the pressure or the flow in a pipe. Okay, so the pipes are defined the normal sort of way with in the drainage network editor you'd be used to, with upstream, downstream inverts, the shape, which is always circular, a diameter, a length, a roughness. So the roughness could be Hayes and Williams, which is probably the most common one. It could be Darcy-Weisbach, which is probably the most academically correct, and it has the other benefit that you can use it to model oil or gas or milk or whatever. Beer, my favourite. It's probably the main difficulty with Darcy-Weisbach is there's not a lot of information on the exponent you use for the coefficient, or epsilon that you use in the coefficient. But I guess you could always use 0.7. So. Chosey-Manning is probably most common for open channel flow, but yeah, if that's your favourite, you can use it. Okay. The other information we associate with a link is a minor loss, so that might be for a reducer or a bend or a meter or some component in your network that will affect flow in some way. Okay. I mentioned pipes can also contain valves. They can react with the flow. Pumps can be defined in terms of power or by a curve. So a pump could just be how many horsepower, how many kilowatts a pump is, and it has an inbuilt equation that it uses to calculate what the head and flow relationship would be for the pump. Or it could be a pump curve, so it could be a single point pump, a 3-point pump, a multi-point pump, a variable speed pump. All of those sorts of components are covered in the pumping system. You can also calculate energy usage and the cost of energy, so you can look at optimising pump systems as well. Valves can be pressure reducing valves, pressure sensing valves, pressure breaker valves, flow control valves, throttle control valves, general purpose valves. If you can come up with another one, we're happy to add it in. One of the big things that you need in an extended period sort of simulation is the ability to control the network. So we have rules and controls that you can add into the network. So it's a if then else, or a if this and that or that, modify it. So here in this example we have 3 rules, right? So if tank level is above a certain amount, then close a pump, and open a valve, right? If but if it's after 8 a.m. or before 6 p.m. and the tank levels below a certain amount, turn on the pump and use your most costly power. Or if the clock time is, if it's after a certain time, before a certain time, and a tank level's above a certain amount or below a certain amount, then you can turn on a pump. And you can modify, you can affect things like nodes, junctions, tanks, reservoirs, pipes, pumps, valves, demand, head, pressure. There's an unlimited number of things really that you can control with rules. Controls are simple rules. They're you can just you can modify only a link, and you can base it on a node condition. So that's a quick and dirty way of of getting a dynamic control into your model. The results we get when we run the simulation is head, demand, pressure, quality, which could be the age of water or a trace, and the status. So you can see what a pump speed is. You can see whether a tank is opening and closing, whether it's filling or emptying, and so on. For the links, we have similar sorts of results. So we've got upstream and downstream hydraulic grade lines. We've got the flow, the velocity, the head loss, the status. So this might be this probably would be the pump speed or valve pressure or something. Settings. So that might be the some of these methods, the roughness changes with Reynolds number or something. So it'll tell us what we're calculating. Reaction rate tells us how water quality is being affected in the model. Friction factor, head loss, so on. We can also do dynamic profiles, so we can show change in head with time. The reason we've got the weird looking network there is just because it connects it shows all the pipes that are connected between two nodes of the link that you've shown. So it's a loop model, so we're seeing the loops there. We also have thematic maps, so dynamic plan results where we have a bubble plot. So the bubble with the node can represent the head or the pressure or status and so on. It'll vary with in size and colour to display the status of the network. You can show that varying with time, or you can show maximum and minimum values throughout the simulation. And the links will vary in size and colour to show what the flow and head loss and so on is through the link. We also have all the standard sort of static plotting facilities that 12D is well known for, with plan plots and long plots and custom text reports and all that sort of stuff with our attributes. So there's minimum, maximum and average values, time-weighted average values for all of those parameters you see in the graphs. They can be used however you wish. There's also some visualisation in it. So with the new drainage network editor, if you assign a tri-mesh to one of the elements of the network, it'll show you that in your system. So you could have a link that's got a reducer in it. You could have a hydrant point chain. You could have a valve in this case, or a pump or whatever. So you can visually see your network. We can also import files from EPANET format, but that would cover all the water supply software that uses that sort of format. So things like WaterCAD, WaterGems, XP Water, Mike Urban, the Innovise products and so on. So yes, quite a broad import facility there. And that's it for me. Thank you.